So a couple of things. You guys had always been in the lead as far as like donations for the class panel. You have now been surpassed by First Block, who is now $5 ahead of you. So if you wanted to do that clothing order, I just need it by Friday. I don't necessarily need the money by Friday, okay? But I'd like to have at least the order by Friday, so that way I can get that in, so that we can start that process of getting everything printed up, okay? So if you don't sit there and go, well, I'm not going to get paid till next week, don't worry about it, okay? Just give me the order and then get the money to me next week. That's going to be the biggest thing. Or if you just want to make a donation, hey, that's cool too. Whatever works for you. But yeah, you guys had always been ahead, and now you're not. No pressure, but I'm just saying. Okay, so here's where we're at. So we've got today and tomorrow on angular motion, and then tomorrow will be angular momentum. And then, which kind of sucks, especially the lecture tomorrow, because the lecture tomorrow is like my favorite lecture to give of all time. And it's really cool because there's so much interaction stuff, and I don't know what I'm going to do, because I'm just depressed about the thought of giving that lecture tomorrow without you all here. And it's just, I just can't even think about it. It's just depressing. Anyway, that's just, we'll get through it. And then we've got a lab. In that situation, I'm just going to have to give you the data, obviously, because you all aren't here. So it's looking like the test over momentum will be beginning early next week, okay? Early next week, maybe the middle, okay? I don't know exactly how this is going to play out, because I'm not sure how the lab is going to play out. So I'm thinking maybe Tuesday, Wednesday-ish of next week for that test. So on momentum. So we'll see how that goes. And then we've got energy, and that'll kind of get us through Christmas. Okay. So a couple of things about rotational motion. So it's kind of old stuff, but it's kind of new stuff as well. So if you look at what happens, hold on, I can move over here. So here I've got like this bicycle wheel, right? So here's the problem with linear motion, is that you have to be able to describe two different situations. You have to be able to describe a situation where you're moving, okay? So I'm going to have what we call linear motion. So the center mass of the bicycle wheel is moving, okay? So I can have motion like this, but I can also have motion like this, where I just have angular motion, but no linear motion. Or if I just take the wheel and just throw it, I could just have linear motion, okay? So those are the three things that we've got to be able to deal with. Just straight linear motion, angular motion by itself, and then the two of them together, okay? So, I don't remember if I started that camera. Give me a second. Okay. I was kind of freaked out because usually there's a little light that blinks when it's on, and it wasn't blinking, but we're still good, because I don't want to give this lecture and then it not have been recorded, which would really suck. Okay, so the other thing that happens is that when things spin, they kind of do weird things. So if I take this is just like a piece of string, okay? And if I hold this up like this, right, and let go of this, it just tips over just like you would expect. However, if I spin it, okay, and then hold it, so then it will stay up, okay, and almost like it's defying gravity, and it begins to what we call precess around like this. Now, if I stop it, all right, and it isn't like I shut off gravity, then it goes back like this. If I spin it in the opposite direction, oddly enough, then it goes in the opposite direction. So, like that. Then it goes around like this. So clearly, something has to be happening. And this is where you can go old school in terms of Newton's ideas as well. This is a pretty low friction bearing surface. So if this wheel is at rest, it's going to remain at rest. If I apply a torque to it, then it's going to accelerate. But then once it gets spinning, it wants to stay spinning until an outside force acts upon it. So one of the things we'll talk about tomorrow is angular momentum. Angular momentum is created by things that are spinning, and we take advantage of that a lot. So like here I've got, hopefully you all can see this. Let me put this up here. So here I've got just like an aluminum top, okay? And if I just set that on there, it just goes doink, okay? So that's kind of like the bicycle wheel. It just goes doink. But if I get it spinning, okay, then it stays upright because now it has what we call an angular momentum vector. Hold on, let me let Kelsey in. Okay? So now it's got an angular momentum vector. And again, just like the wheel, it's going to keep spinning and spinning and spinning until an outside force acts upon it. So there's a little bit of friction between the surface and the aluminum, and it's going to slow down a little bit. And as it slows down, it begins to wobble. Because as it slows down, it kind of loses that angular momentum, and it can't stay upright, and it begins to wobble. So eventually, here before too long, it's going to like crash and burn. Hold on. By the way, if you really want, it's called Forever Spin. If you do a search on it, you can spend a lot of money at this website. I'm just telling you. Like this one's made out of aluminum. This one's really cool. It's out of what's called Damascus steel, so it has like a really cool shape to it. And you know, you can do that one as well. So anyway, I'm just telling you, you can spend a lot of money there. All right, so the other thing that's going to be different about this is that we have to introduce a new set of variables. So we're going to introduce some Greek letters. So basically, all the linear motion variables have already been taken up. So the angular motion guys said, all right, hey, you know, we got to come up with something different. So they started using the Greek alphabet. So I set out the assignment, and on the front of that assignment, there's some equations and some variables. So the big three that we're going to use is going to be theta, omega, and alpha. Now, theta, okay? Now, let's just get this straight right now, because if I don't say this, one of you is going to think this, and you're going to think that you're the most clever person in the entire world who's ever come up with this idea. And you're going to go, that looks like a butt, okay? So, you're not clever. Everybody realizes it looks like a butt, okay? All right, so, and this looks like a fish. So, we have theta, butt, fish. If that's how you want to remember it, that's fine. I don't care. The Greek gods are not happy with you because that's how you're remembering it, but I don't care. Don't sit there and go, it's a butt. I know it is. It's okay. Everybody knows that. All right. So, theta is going to be measured in radians. So, let's talk about radians. Radians are kind of this weird way of measuring things that move in a circle. Radians are what we call a dimensionless number, okay? So, and for those of you that have done trig or pre-calc, I'm sure you've dealt with radians before. But let's view it from a physics perspective. So, so let's say that I've got this piece of tape like right here. And that one's probably easier for you to see. So I've got a piece of tape right here. And I'm going to make that thing go around until it gets back to this point. So that's going to be 1 revolution. So here's the one big conversion that you need to remember, is that 1 revolution is equivalent to 2 pi radians. Okay? Now, radians are a dimensionless number. It isn't like I'm going to say, oh, it's 5 meters or it's 2 pi meters. Okay? 1 revolution is just 2 pi radians. Now, one of the things that you'll see is that you have to decide, is the size of the wheel a factor in determining some of these quantities? So if I've got a bicycle wheel and it goes around and it makes 1 revolution, that's 2 pi radians. If I've got a golf ball like this, okay, so I got this little line right here. If I make that line go around and get back to that point, that also made 1 revolution. That's also 2 pi radians. If I look at the Earth as it spins on its axis, the Earth spins once on its axis, that's 2 pi radians. The Earth goes around the Sun, that's 1 revolution, still 2 pi radians. Okay? So 1 revolution is always 2 pi radians. The size of the object does not matter. Okay? It's a set conversion. 1 revolution is 2 pi radians. That's it. There's nothing to think about. Okay. So theta is similar to a linear idea of distance. Okay? So if I were to talk about, oh, how far did I walk? 5 meters. Okay, it's a distance. If I talk about this wheel and how many radians it moves through, that's a similar type idea. So distance and meters is equivalent to theta and radians. Did it just make a part of a revolution, or did it make multiple revolutions? That's the same idea. Now, omega is how fast you're going to spin. So this is going to be in radians per second. Okay? So I can have this wheel, and it can spin very slowly. So this would be a small number of radians per second. Or I can have it spin very quickly, and that would be a large number of radians per second. So depending upon the situation, it's either going to spin slow, it's going to spin fast. Obviously, the bigger the number is, the faster it's spinning. Okay? Now, just like you can only use velocity as distance divided by time, Adam and Hewer, what's the only time that I can take distance and divide it by time and get my velocity?
I have no idea.
Sweetheart, you're killing me.
Also, I'm driving, so I'm only like half paying attention, to be honest.
Okay, all right. I appreciate the honesty. So, party girl, what's the only time that I can take distance and divide it by time and get velocity?
If you have constant acceleration.
Can you see my squinchy face?
I do.
Okay. It is, you are right, that it is constant, but it's not constant acceleration. It rhymes with constant velocity. Party girl.
Constant velocity.
There you go. Perfect. Well done. Okay. Because if you are accelerating, then your velocity is always changing. So just like you can only take displacement and divide it by time when you have constant velocity, to get omega and take theta and divide that by time, you can only use that if a wheel is spinning at a constant rate. If, like for example, the Earth spins at a pretty constant rate, thank God. Okay? Now it's actually slowed down. They figured, and I don't know how they did the math or whatever, but they figured when the dinosaurs were around, a day was actually like 20 hours, okay, because the Earth has slowed down as it spun. But so for the sake of what we're going to do, we're going to assume that the Earth is spinning at a constant velocity. But it's actually slowing down, and they have to make adjustments to atomic clocks every once in a while. Okay, so The only time you can take theta and divide it by time to get your butt is if you're spinning at a constant rate. If you're speeding up or slowing down, you can't do this. Now, speaking of speeding up and slowing down, you have alpha. So this is your acceleration. So this is going to be radians per second squared. So here's the basic idea. You're going to go radians per second, radians per second squared. Distance, velocity, acceleration. So, and again, it's a lot of the same ideas. Just like velocity is only distance divided by time when you have constant velocity, guess what? Anytime you have an equation like you have distance equals 1/2 at squared plus v naught time, you can come in here and do a substitution and go, oh, theta would equal 1/2 alpha t squared plus, and this is just fun to say, but not time. Okay? So, anytime you have a velocity, you insert your but. Anytime you have an a, you put an alpha. Anytime there's a distance, you put theta. It's the exact same idea. Just like if you have a velocity time graph like this, and this shows it speeding up, and the slope represents acceleration. If you have a, wait for it, a but time graph, and you have a slope like that, that slope is going to give you your acceleration. You would have positive acceleration with positive angular velocity. You're going to speed up. If this line was coming down like this, you would have negative acceleration and you would be slowing down. And just like on a velocity time graph, that area is going to give you displacement in meters. The area here would give you theta in radians. So everything that we've studied in terms of graphs is the exact same idea. Okay? Slopes are accelerations, slopes here are accelerations. Area here is displacement, area here is displacement. That's just in meters, that's just in radians. Okay? That's the only difference. All right. So, with that said, that's the basic idea. Now, you're going to have 3 crossover equations. And if you need these for the test, I will give you these equations. Don't memorize them. But you have d equals r theta, you have v equals r but, and you have a equals r alpha. So what these 3 equations do is that they allow you to cross over between a linear distance and an angular, between a linear velocity and an angular velocity, between a linear acceleration and an angular acceleration. Now, here's what's important. Notice on all 3 of these that they're dependent upon radius. Okay? All 3 of these are dependent upon the radius of the wheel. And on all 3 of these is if this side remains constant, as the radius gets bigger, these values are going to get bigger. So let me show you a simple example. Okay? So I'm going to take this bicycle wheel, and where's my little piece of tape? I need to put on a more colorful piece of tape. Here, this one. Okay? So I'm going to start here. I don't know if you guys can see that or not, but I'm going to start here with that piece of tape at the bottom. And I'm going to roll it along through 1 revolution until it gets, I don't want to run over Al, until it gets back to the bottom. Okay? So I'm going to make 1 complete revolution, and what I want to know is how far the bicycle wheel traveled. So, now, for now, I want you to all to pretend that those equations don't exist. You don't know anything at all. Okay? You don't know anything about what we've talked about. Here's what I want you to know, or here's what I want you to think through. How could I figure out how far the bicycle wheel would travel? What's one thing that I could do? So I'm going to make this bicycle wheel make 1 revolution. So what's one thing that I could do to figure out how far it's going to go? in one revolution? Ryan Fullerton.
The circumference.
Beautiful, okay? I can find the circumference of the wheel. So imagine that I could take a piece of string and I could wrap that string all the way around the wheel one time, and then I could stretch that string out, and then that would be how far the wheel would travel. Now, Mr. Fullerton, how do you find the circumference of a circle?
It's really slipping me right now.
Let me give you a hint. It starts with 2. It starts with
2 pi r.
2 pi r. Beautiful. Okay? Circumference of a circle. Now, let's say that this wheel has a radius of 0.25 meters. So if I wanted to find the circumference of this wheel, I would take 2 pi times 0.25 meters. Now, this is where math people and physics people tend to deviate. Math people are going to tell you to leave that answer in terms of pi, because they're going to go, oh, that's more precise because it's in terms of pi. And purely mathematical, they are spot on. Okay? That is a perfect answer mathematically. But here's the problem. Okay? I can't find a meter stick that's measured in units of pi. I can only find meter sticks that are measured out in decimals. Okay? So pi does give you a more pure mathematical answer, but you can't measure something with a meter stick marked off in pi. Okay? That's the problem. So, out of curiosity, somebody get out a calculator and get me this answer in terms of like an actual decimal. So take 2 pi, which is going to be pi divided by 2, which is going to be 1 point something. Beautiful, 1.57 meters. Okay? And that's about how far it is across the edge of my table, 1.57 meters. Now, if I went 2 revolutions, guess what? I'd go twice as far. Okay, well that's pretty simple. All right, so that's one way to view this. Oh, it's the circumference of the wheel, but you're going, oh, but Mr. Burkham, we have these cool equations up here. Do those work? I don't know, let's see. So if I want to try and use the cool little crossover equation that says d equals r theta. So theta, because I made 1 revolution, is going to be 2 pi radians. So now I know what theta is, okay? I know my radius is 0.25, so I'm going to have 0.25 times 2 pi radians. Now, radians are this dimensionless number. They float in and they float out. So notice that I'm going to do the exact same math as finding the circumference if I made 1 revolution. I'm still going to get 1.57 meters. So if I wanted to find the circumference, it's 2 pi r. If I'm going to make 1 revolution, theta is going to be 2 pi. I multiply that by 0.25, boom, I'm off. Now, here's the cool thing. This is actually a linear relationship. And you go, Burkham, you're nuts. That's so not linear. Well, look. I would argue that it is. Because I'm going to graph I'm going to graph how far it's going to travel on the y-axis. I'm going to graph theta on the x-axis. So here's what we had. We had 1.57 meters, okay? And we had theta, which was 2 pi. Now, if I made 2 revolutions, I would go 4 pi, and that would be like 3.14. Oddly enough, that would be pi. Now, here's the cool thing. Lauren, do me a favor. Take 1.57. I want to find the slope of this line. So, Lauren, take 1.57 and then divide that by 2 pi. Now, let me give you all a hint. You're going to do this conversion a lot. When you punch in divide by 2 pi, put that in brackets, because if you just punch in divide by 2 pi, what your calculator will do is divide by 2 and then it will multiply by pi and it'll screw up that order of operations. Okay? So Lauren, what'd you get when you took 1.57 and divided it by 2 pi? Yeah, you got 0.25. Oh, look, how cool is that? That's the radius. That's the slope of the line. So this is a linear function. Here's your y values. The slope is the radius. Here's your value theta. Now, here's what I want you to think through. So this was this big wheel, right? So now I'm going to do the same thing with Gary the golf ball. Okay? So I'm going to have Gary go through one complete revolution. Okay? So theta is going to be the same. But what do you notice about the radius of Gary the golf ball? It's really, really small, right? So even though Gary is going to go through one revolution, Gary isn't going to travel near as far. So here's the deal. Let's say that his radius is 0.025, just to make the math easy. If his radius is 2.5 centimeters, which is about like yay, if you go to this graph, and at one revolution, 2 pi, he's only going to go like 0.157 meters. Oh, right. That line's going to be a lot more shallow, because this line's going to be a lot more shallow because that radius is smaller. So here's what I want you to look at, okay? If Gary makes one revolution, he travels through 2 pi radians. If the wheel makes one revolution, it travels through 2 pi radians. But the linear distance that Gary, the golf ball, travels is much smaller than the linear distance than the bicycle wheel travels. So that's why I said you have to look at what you're holding constant and what you are changing. Okay? That's going to be the big kicker. All right. Got that. Now, let's move on to V equals R omega. Now, you do not know this, but I'm going to show you why this is true. Every time you have driven a car, you have taken advantage of V equals R omega. Okay? And you'll see why this works. So, I'm going to take this wheel, okay, and I'm going to make it spin, and I'm going to make it spin through, I don't know, let's kind of go fast, 2 revolutions per second. Okay? So, I'm going to make this wheel spin at 2 revolutions per second. Now, here's the deal. If I'm spinning at 2 revolutions per second, I need this omega to be in radians per second, not revolutions per second. So, here's the big question. Rachel Meeker, I need to get revolutions per second into radians per second. So what can I do? By doing what? That's a beautiful answer, but what do I have to do? Remember, 1 revolution is 2 pi radians. So how am I going to use that to find my number of radians? Can I give you a hint? It rhymes with multiply by 2 pi. Oh, I hate Zoom. Oh, God, I'd kill for you guys to be back in the room. Okay, so Rachel, I'm going to give you the benefit of the doubt because I know you're brilliant, and I'm going to assume. Okay, all right. Okay, so here's what I know exactly what Rachel was thinking. Rachel was thinking this. She's going to go, oh, Mr. Burkham, we could do a conversion where 1 revolution is 2 pi radians. And the revolutions are going to cancel out, and I'm going to end up in radians. So if I multiply this across, I get 4 pi radians per second. Now here's the problem. You all aren't used to thinking in terms of radians per second. If I say, hey, I'm running 5 meters per second, okay, that's something that you all can understand. Oh yeah, 5 meters per second. I've seen Burkamp run. Okay, he's old, he doesn't really run that fast. But radians per 4 pi radians per second, you're going, man, what does that even mean? So this just kind of give you a perspective, right? So that's spinning like that. That's probably way too fast, okay? Probably more like that. So that's spinning at about 2 revolutions per second, which would be 4 pi radians per second. Now, so here's the deal. So if this wheel is spinning at 4 pi radians per second, I want to figure out how fast the wheel is moving as it travels down the road. That's what I'm trying to find, okay? So, here's the deal. The radius was 0.25, so I'm going to take 0.25 meters, and then I'm going to multiply that by 4 pi radians per second, okay? Now, mathematically, I'm going to take 0.25 times 4, okay? 1/4 of 4 gets me 1, so I get pi, right? So this is pi meters per second. When you do this, don't write this as like meter radians. And I know I've preached to pay attention to the units. This is a dimensionless number. So don't take meters times radians and go, oh, I get meter radians per second. Radians are like ghost units. They kind of float in and they float out. So this is just going to be meters per second. I don't want to leave it in terms of pi. So I'm going to have 3.14 meters per second. Okay? There you go. Now, clearly, the faster this goes, the bigger your linear velocity is going to be. So this is where you have used this every time you've driven a car. And you go, Burkamp, I've never seen this equation before in my life. Yeah, you have. You just don't know it. So here's a quick lesson on automotive things. So here's your engine on the car, and it transmits power to your transmission, and then your transmission transmits power out to your wheels. Okay? Now, if you look on the inside driver's side, there's going to be a label, okay, in the inside driver's door. There's going to be a label that's going to list the size of tires that your car is supposed to have, and like air pressure and things like that. So here's how your speedometer works. Your speedometer works off the idea that V equals R omega. Okay? This is how your speedometer works. So what happens is that there's a sensor somewhere, either in your transmission or somewhere, that picks up the rate at which something is spinning inside of here. Okay? A gear, a shaft. It's picking up how fast something is spinning. So it's going to know omega. Now, the R is going to be the radius of your tires. Okay? So this is going to be calculated based upon a certain size of tire, which is going to translate into a linear velocity and of how fast you're going down the road, and it's going to say, oh, you're going 40 miles per hour. Okay? So this equation is based off a certain size tire that you're supposed to have on your car. Now, let's say, hypothetically, that you're going through this rebel stage, which I doubt happens to any of you, but let's just say that you're going through your rebel stage, and you're breaking the law, right? You're speeding, okay, and you're getting all these speeding tickets. Your mom and dad are about to kill you, and your insurance company is about to drop you. But it's like, oh man, I got to drive fast, okay? I got to look cool to my friends. By the way, you need to get new friends. So it's like, oh, I still want to be cool. So what you can do is take your normal size bicycle tires, your normal size tires, and put much smaller wheels on them, okay? So here's what's going to happen. You put these smaller wheels on here, the car is going to think that it still has this size of tire on it, based upon that size of rotation, but in reality, you're going to be going much slower because with each spin of the wheel, you're not going to go as far. So you can still look cool and go, oh, look, I'm breaking the law. I'm driving 40 miles an hour. But in reality, you're not going to be going that fast because of the fact that for each revolution, you're not going to go as far. Now, this notoriously happens to guys, and you don't see it as much. But guys notoriously buy trucks or Jeeps and they put big oversized tires on them, okay? So here's what happens there. It's just the opposite. So if you put oversized tires on your car, then you're going to think that you're driving 40 miles an hour, but in reality you might be driving like 45 or 50 miles an hour. And then you're going to get pulled over and the cop's going to go, hey, you were driving 50 in a 45. And you're going to go, no, I was only driving 45. And the cop's going to go, wow, don't you know that V equals R omega? And so help me, if you're one of my physics students, and you go, Mr. Burkamp never taught me that equation in my life, I will personally go to court and testify against you. And go, that's a bold-faced lie. He's lying, hold him in contempt of court, and give him a major ticket because he knows better than this. So, if you're going to be putting on big tires on your car, your speedometer is going to lie to you. You're actually going faster than what the speedometer is showing. So, but if you have that same size tire, then it's not going to be an issue. So, you can also have like A equals R alpha, okay? So, typically how this one plays out, this is going to be your linear acceleration. So if you know that your car is accelerating at a certain rate, and you know the radius of the tires, then you can calculate, oh, what's the angular acceleration of the tires. So here's what I want you to see, is that you've got these big three equations, theta equals R alpha. Excuse me, I screwed that one up. D equals, oh come on, R theta, V equals R butt, A equals R fish. These values are dependent upon your radius. These values aren't not. So, here's what I want you to get out of this. If I've got Gary the golf ball spinning at 1 revolution per second, that's going to be the same number of radians per second as this bicycle wheel spinning at 1 revolution per second. Obviously, the linear distance, the linear velocity, the acceleration, those are going to be completely different based upon a radius. So you have to remember what's dependent upon a radius and what's not. Okay, so here's the last big thing, and that's going to be torque. So on your equation sheet, you've got, oh, I gotta find it, they always keep this thing hidden. Okay. Okay. So on your yellow equation sheet, kind of over here, right underneath where it talks about like, it's got like theta, and then it's got omega, and then it's down about 2/3 of the way down here. Okay, and it's random how they arrange the sheet. I hate how they arrange it. It doesn't make any sense, but here's where it is. So, this is a situation where you use torque all the time. You just don't know that you use torque. So let me give you a simple example. So here I've got a simple meter stick, okay? That's, I'm going to try and balance out, which is pretty tough to do. Okay, there I've got everything balanced. So, when something balances, you have two types of torque. So, and as you all shift to a digital age from like the old style clocks, I've got to like introduce clockwise and counterclockwise. So this one, okay, is pulling this way. So this is what we call a clockwise torque because it wants to move it in the direction that that hands move on a clock. This one over here is pulling down this way, and this is a counterclockwise torque. So here's what's happening. First off, if you look at these equations, the only way this thing can balance out is if these two torques are equal. So here's the deal. So this sine theta is referring to the angle that it makes with the surface. So this is at 90 degrees. The sine of 90 is 1. We don't have to worry about that. Okay? So generally, the only time you have to worry about that sine is when I would like push down at an angle like this. Okay? And then it would only, if I push down at an angle like this, it's only this component of the force that's going to be generating torque. The part that's going this way isn't. So that's the only time you have to worry about this. So that's why they have this R with the perpendicular, because this is your radius and it's at a perpendicular angle, and this is going to be your force. So if you look at the units, okay, well, that force is going to be in newtons, that radius is going to be in meters, so torque is measured in Newton meters. So here's what's happening to balance, to make this thing balance. So basically what I've got, okay, pretend that this thing is balanced, and it basically is. So basically what's happening, here's my point of balance. So I've got this, right? Here I've got a big force because I've got a big weight and a small radius. Out here I've got a big radius with a small force. So this is what's balancing this out. So here I've got a small radius, but I've got a big force. Over here I've got a big radius with a small force. Now, if I actually want to calculate the force, oh, hey, gravity's doing the work. So this would be mass times gravitational acceleration. This would be mg. So if gravity is what's doing the work, it's going to be the weight times your radius. So this is what's going to allow this thing to balance out. Now, I'm going to move over here. I'm going to take the camera and I'm going to move it over here so you can see what's going on with the door. So give me a second. Hopefully you all can still see the door. Yeah, you can. Okay, cool. All right. So, assuming that at some point you all would actually get to be back in this room and I could actually get to teach you in person again, which is going to be pretty cool. I'm kind of hyped about that possibility. And so let's say you go to open up the door. So there's two places that you could push. Option number one, you could push right here beside the hinges. Option number two, you could push way out here. Now, you all have been in this room, and you all push out here. Okay? And the door opens pretty easy. I could open the door by pushing right here. Okay? But I've got to push really, really hard. Now, here's what's important. It's going to take the same amount of torque to open up this door no matter what. Okay? So that's going to be the same. So, if I push out here, I just have a big radius, so I don't have to apply as much force. Here, I've got a smaller radius. I'm going to have to push a lot harder because I've got a small radius, so that's going to require more force. So, that's why I said every time you all have opened up a door, you've used torque. Okay, so let me kind of change everything back here. Okay. There we go. Wow. Okay. Now, let me kind of get you started on the assignment that I sent out, okay? So, I want to make sure everybody's cool with how this thing is going to start. So, on number 1, okay, I've got, if the tip of a second-hand watch is 12 millimeters from the axis, what's the linear velocity at the tip? So, let's start with this. So, number 1, you're talking about the second hand on a watch. So let's start with this idea. The second hand is going to make 1 revolution. So I'm going to use theta divided by time. So theta is going to be 2 pi. So how long does it take for the second hand to make 1 revolution around the clock face? Diego.
60 seconds?
Beautiful, 60 seconds. The hour hand, oddly enough, takes an hour. Excuse me, the hour hand actually takes 12 hours, the minute hand takes an hour. Okay, but the second hand takes 60 seconds. So to get omega, I'm going to go, oh, that's 2 pi divided by 60 seconds. So notice that this, what we call our angular velocity, is not dependent upon the radius. I didn't have to tell you the size of the second hand on my watch. So whether this is my watch, whether it's the second hand up there on the bigger clock on the wall, whether it's Big Ben in downtown London, any second hand on any watch in the world is going to travel 2 pi radians in 60 seconds. Okay? That's going to be the same no matter what. But what I want to know, and you have to get used to the terminology, so I'm asking, what's the linear velocity? So the linear velocity would be like, imagine that you could shrink yourself down like in the movie Ant-Man. You're going to shrink yourself down, and you want to know how fast you would have to walk to keep up with that second hand. Or if you could visualize it and you could have a radar gun, and you would want to know, hey, how fast is the tip of that thing moving in meters per second? So what you want to do on number 1, here's going to get you omega. So it's going to be 2 pi divided by 60 seconds. And then you're going to use V equals R omega. So here's going to be your omega. Here's your radius. Now clearly, as the radius gets bigger, so if you had a bigger watch, the end of that hand would be going faster because it would be traveling a greater circumference in the same amount of time. Okay? So that's what you want to think through. When you get to question number 6 on the bottom of this front page, you have a board like this, and you get to decide where you put the fulcrum. Okay? So let me give you a hint on how you ultimately want to end up using number 6. The total length of this thing is 1.75 meters long. So this, at some point, here's what you need to do. Pick a distance x, okay? Because you're going to have 2 torques. You're going to have the torque going this way is going to equal the torque going this way. So on this one, it's kind of like the, in some ways, it's like the Lagrange point problem that you did with the moon. So if you let this distance be x, so this is going to be some force times x, this is going to equal that other force. Now, if this is x, and the total length is 1.75, what's left over is 1.75 minus x. So it's like the Lagrange point. Oh, you had the distance to the first Lagrange point, and then you had whatever was left over minus x. So you're going to have, like for example, this is George and Joe. So this could be the force of George times x is going to equal the force of Joe times 1.75 minus x. So that's going to turn into an algebra problem. You've got the mass times g, you have mass times g. If you work it out with variables, you see that this becomes simple because you can cancel some things out. There's some problems out of the back of the book, and when you get to this first question on number 3, in the book, this will make sense when you get to these problems. Your book defines clockwise as being negative value and counterclockwise being positive, okay? So keep that in mind when you get to question 3 in the book. Clockwise is negative, counterclockwise is a positive value. These are pretty simple to do. They don't take up a whole lot. That won't take up much space. Okay, I'm done. We're about out of time. I'll get this video uploaded after school as soon as I can. Thank you all for your time. Don't forget, Friday, if you're going to make the orders, I just at least need the orders by Friday, and then you can pay me later. And again, no pressure, but you guys aren't in the lead anymore. So keep that in mind. Okay, all right. See you, kids, and we will chit-chat tomorrow. Stay safe, especially if it snows.
See you, Bert.
See ya.